last talk of the day is going to be on defending malicious clients in federated learning with blockchain by Shuoying Zhang. And there's also another session going on simultaneously in the other room on revolution towards decentralized academic publishing
do you work
by
we should talk about it after. Yeah, I'll come closer. Please do. Yeah, that would be wonderful. Thank you.
So, plug you in. So basically, just try and stay in front of this one. I'm just like blindly trying to whack this in. Do you have notes or anything, or do you wanna? Oh, you can do just this one. It's gonna show it in a second, but basically it'll show up on this screen. This is what everyone's seeing. I don't know why it's not showing up. Oh, it's asking for permissions. Let's try it again. Weird. Trouble with these. It's okay. I also shared with you on the Google Drive. This one doesn't work. Yeah. This is on. So strange. Did I need to turn on anything or? Maybe something where it's like blocking like outside sources or something. I'm not. Do you have a backup? Yeah. Yeah, it's not responding. Yeah, I shared it. Hi. No. Something to do with my settings.
We'll try another reconnect. You don't have a HTML. Oh, there is one there.
But like sometimes I ask for permission for your next like flash for a second.
All
right. I didn't ask anything. Well, this is an HTML thing if you want to try it with this. Oh, that one.
Yeah, probably this one.
It looks like it's.
It should come up on this. Oh, there we go. Okay.
It hasn't come up on the big screen.
Oh yeah, I'll have to do that myself manually when I get back up there.
Thanks so much.
No worries.
Okay. I'm just waiting, right? Yeah, cool. Yeah, no, it's fine. Ooh, it's happening. Hi everyone, super grateful to be here and thanks for staying to the last. Today I'm presenting Flock, which is a startup I co-founded firstly with a group of friends from Oxford, and now we're a loose association of somehow 10, 15 people. We are doing this on-chain federated learning thing, and we're doing it in 2 steps. So firstly, ensure that everyone who come with a good intention can separate themselves from the people that have bad intentions. And secondly, ensuring everyone can do so in an efficient manner. And this is the first step, which we've just concluded the R&D stage for. You can actually Google, we've published a paper with the same title, and it just won the Best Paper Award in Europe's blockchain workshop. Some people call it a NIPS. And this is in the middle of engineering. So what we're trying to do, I think the benefit of talking last is that you probably are already familiar with the problem. So there is a growing tension about the need to feed the machine learning models with more and more data and data privacy concerns. We know data breaches are on the rise, so this is not just enterprises. Even for myself, I have experienced data breaches from British Airways, Marriott, so my personal data probably on a dark web somewhere. Current standard solution is anonymizing my data and sending me a big consent form saying use at your own risk. But we already know re-identification attack, which traces your identity from your attributes, is very effective. Like people published papers about it 10 years ago, but still this is a standard practice. And if you work as a researcher, you should know better than I do that sometimes you would like to access the data and those people want you to do so, but you can't because of regulatory restrictions. In healthcare, we have the HIPAA. In other areas, GDPR. So before this, I used to work in consulting, and I've seen firsthand the bank branches, they want to cooperate and train a fraud detection model, but they couldn't share the data because country regulation require customer data stay in the domestic server. So in the end, African countries have a less effective algorithm compared to their European peers just because they don't have enough data. So this is a problem we're targeting. We think federated learning is a promising solution. Now, a few projects have touched on it. I'll just quickly introduce what it is. Basically, the tagline is, while you're training the model, the source data stay at source. So you see here, we deploy a local model to each data source, and the data source, while training those models, they come up with how you can improve the performance. We call them model updates or gradients. And the interesting thing here is only the gradients are shared among local models, so the source data stay at source. Currently, in the current framework, the model updates are aggregated on a central server. So it's either hosted by the federated learning organizer, or in the case touching on like a big tech company. So the most famous example is Google Keyboard. And those of you have Android phones, you probably are using it for like 5-6 years. Basically, like touch screens are very fiddly, and we need a way to predict the next word or sometimes autocorrect. In the case of my name, it's always getting autocorrected to something else, but that's a side note. Interestingly, people's text messages are very private information. We definitely don't want to send them to Google for them to train a next word prediction algorithm. So Google deployed a model for next word prediction on our phones. So you are tuning the model while you text, and only the model updates are shared to the Google server. Apart from Google Keyboard, there is also applications in other industries. What we're trying to do at Flock is to make this happen on a bigger scale and enable smaller organizations to also conduct federated learning. And while you're trying to roll out a framework that comes from a walled garden, maybe Android or iPhone or even Meta, you always run into the problem of, is it going to work in the wild? So we know TensorFlow federated behind Google is very powerful. It powers the next word prediction algorithm I was talking about. Similarly, Meta has its own framework and FedML, etc. But if you're running it in an environment that you don't control, you always had to worry about malicious participants. So while I'm the data source and I participate in the model training process, I might have various malicious intents. So imagine your algorithm is, we talked about like in healthcare, like drug discovery, and I'm a competitor pharma company. I might participate just to drag you down. I might participate with poison data or sending random updates so that your final model is not effective, and I can defeat you in this drug race. Or it could be, you know, I'm just someone who is wanting to have a ransom. So I say, I can send you so many meaningless updates, so sort of like a DDoS attack, and I only stop if you pay me a ransom fee. Or I can just send you like wrong upgrades for no reason. So, you know, like malicious clients, they can impair the model performance significantly. And this is an issue we need to solve if we want to have federated learning running in the wild or in the more open environment. Currently, this problem is not surprisingly not very well targeted because the companies who use most of federated learning are the big tech companies that we know about, and they control the data sources. What I mean is, you know, when Google built the algorithm for next word prediction, it knows from which area it can collect the raw updates. And if there is a malfunctioning, can shut down that channel. But for smaller companies, maybe research consortiums, they don't have the same level of control over data sources. And this is currently leading to like a post hoc correction. So if I see abnormal updates, I might consider shutting down that client. But if you have a lot of clients, then the monitoring become a huge effort. So we see this problem is effectively about trust, you know, trusting your clients to behave, trusting your peers to have the same level of good intention as you have. And we know like blockchain is a good trust engine. It can manufacture consensus using crypto economic incentives. So more specifically, I'm talking about the proof of stake mechanism. So I guess you guys are all familiar with it, but briefly, you have put on a stake to do something, and there's a corresponding reward slashing mechanism that is decided upon peer decision, peer review, and you get rewarded if your behavior contributes to the system and slashed if otherwise. We also find that an on-chain solution brings other benefits to federated learning as well. So if you imagine, if you remember, in the traditional federated learning, the model aggregation happens in a central server, and obviously there's a lot of cost hosting and maintaining that server, but we can do it on a smart contract. So you don't have to trust a central party doing the aggregation correctly. You don't have to invest a huge amount of money because the central server is a single point of failure. Also, like a lot of literature in federated learning is about bandwidth and communication costs between the client and server. If the model updates are sent on-chain, then it's direct peer-to-peer communication. So how it works in a high level, we have two participants. So you see on the top row, we have proposers of model updates, and the bottom row, they are sort of the voters or validators or assessors of the model updates. So to start, you have participants, every participants, they need to put down a stake so that we can punish them or reward them if they behave or misbehave. And the proposers, they conduct local training. So the training isn't happening on chain. They only send the model updates on chain. And once it's aggregated, the on-chain aggregation step is a simple like weighted average of local updates. And once step 3 is completed, you have the community of voters voting on aggregated updates. And they can have a positive vote if they find model updates improve model performance. And then the updates get incorporated to each local model. If it doesn't improve model performance, it's a negative vote, and that particular update gets rejected. So broadly, I think we're all pretty familiar with maybe the first step and the second step, you know, like staking and off-chain training. I'll just focus more on how the proposer and voters work in a proof of stake setting. So, a question I often get is how do you assess the quality of the update? So we do it in a peer-to-peer way. So while training, each node have to leave a portion of data as holdout data. So this is quite intuitive for those of you who work in machine learning. You always have part of data to train and part of data to test. They do the same. So once they receive updates, they will test it on their holdout data. And if they find it's a good update, they give a good score, if not a negative score. And then the votes are aggregated. If it's above a threshold, the update gets incorporated. If not, the update gets left out and people who propose the update get slashed. So that's a voter. Yeah, so how do we tackle malicious client in this case is that if you imagine in each machine learning training round, there are multiple rounds of training. And for us, it's a multi-round game. So if I'm a proposer and I consistently send bad updates, I'll get slashed in each round. And over time, my stake will run out. And that means I'm no longer qualified to play in this game. And that's how the malicious client gets filtered out. And if you think about like the process as a whole, you basically can trust that if I participate in this round of training and there are people with malicious intent, they might poison one round of data, but that's fine. Like to get a good performance, you probably have 70 and 80 rounds. And over time, those people will be filtered out. And I can trust the process happening without a central coordinator and without trusting like a particular server stored somewhere. Yeah. So I guess that's a point of decentralized security. So whereas Google keyboards, you rely on the security and good functioning of the server stored in Google. In here, you just trust the smart contract for reward and slashing operating as it should, which you can always check and even run a client yourself. Also, the flip side of malicious client is hardworking or good clients. Those people, if their updates get incorporated, they will get a reward. So this is quite a granular reward because in each round, if you are contributing, you get a reward. So I guess it links to the data and how data get funded point we talked about earlier. And finally, because of aggregation for model updates happen on-chain, you have a verifiable audit trail, like who is sending a bad update, who is sending a reasonable update, you can trace. I think that's our system overall. And if I can just advertise a bit, so thank you. We are looking for builders of all sorts. So currently this system is being engineered, and if you're a machine learning engineer, federated learning engineer, or blockchain developer, or like builder of a different sorts, please talk to us. We'd love to show you what we're doing and have everyone contributing. Thank you.
Great, thank you so much. So we have a few minutes for questions. If there are anybody, yes, over there. It's a long way, but Alex is, yeah, she's on top of it.
Is there an on button? Oh, there we go.
It takes a second.
Yeah, so is there a threshold for the staking and slashing? So say, for example, sorry, actually, I should start with another question. Are the updates counted before a person is filtered out? So, yeah, if you could answer that one first, please.
Yeah, so this filtering out is like an ongoing process. So each update needs to be aggregate first, so then people can vote on. Does that answer your question?
Yeah. So then the follow-up question would be, is there a threshold for staking? So say I was a bad actor and I allocated X amount of tokens because I decided it was worth that amount of money to sabotage you. Could I still basically maliciously act on your system by staking enough tokens before getting?
Yeah, good question. So like the system in the paper with the same title, we talked about different system parameters. So you have staking threshold, reward ratio, slashing ratio, and threshold for aggregate score to count an update. So depending on how much you trust the participants and how important it is to filter out malicious update, you can raise the threshold for staking, you can raise the reward, you can raise the slashing ratio. So this set of parameters are all configurable. If you think there might be some bad actors with really strong intention to derail the model, I think you can just raise the threshold for staking and slashing ratio.
Awesome, thank you. Can you send me a link to that paper as well?
Yes, it should be the same title.
Okay, yeah, I'll look at it.
But I'll send it to you later. Yeah.
Thank you.
Right.
Tremendous, huge fan of your guys' architecture and everything, everything you guys are building. What I'm curious for machine learning developers, if they're used to using PyTorch or TensorFlow, any of those technologies, should Flock integrate with those tools, or do you guys provide different libraries for them? I'm curious what the onboarding process should look like.
Great question. Yeah, exactly. For the easy onboarding, the system is built with PyTorch. So anyone who knows Python can use it. There are some readily available frameworks like TensorFlow, federated, or fedML, but then that just creates additional barrier because people have to learn those frameworks. But having said that, I see our value add here is more like incentive consensus mechanism. So we're open to be integrated with any of those federated learning frameworks. If that answers your question.
That's great, thank you.
And thanks for the talk. So one thing that worries me about federated learning is like, isn't there a risk of basically the data leaking into the model so that you can potentially even extract the data from the model?
Yeah.
So what are your thoughts on that?
Yeah, definitely. Model inversion attacks have been one of the bigger issues. So in this one, we're more about creating a decentralized and secure environment, but we have a research strand looking into how to counter the model inversion attacks, which is basically working out the raw data from the model updates. And this also has been proven, well, not 8 years ago, but 2 years ago, that is easily done. Our approach is, basically doing two things. So firstly, we do compression. So instead of sending the full set of gradients, you compress and only send a fraction of that. Interestingly, if you think about model updates, not all the updates are meaningful. So that's what backward propagation can rank the most meaningful updates. And if you only send those ones, it's harder to reverse engineer the data. And secondly, it is more about encryption and using either homomorphic encryption or k-anonymity, those kind of privacy measures. And finally, there's something quite new that we're playing around with. You can have mix-up on the gradient updates. And this is, to be frank, something I don't quite understand.
What, sorry?
It's called gradient mix-up. I can put in touch with our research engineer. He's writing a paper and furiously doing experiments at the moment. But k-anonymity and homomorphic encryption, I know that is new to me as well. Yeah.
Great, thank you so much. Okay, I guess that's it for the first day of DeSci London. So as I mentioned earlier, there's the drinks at the Lighterman. I keep on saying Lighthouse, Lighterman. There's more information on the Telegram group about that. So yeah, looking forward to seeing you all tomorrow as well.